A hidden force at the center of most galaxies controls their ultimate fate. This force is an active galactic nucleus, a cosmic engine powered by a supermassive black hole. By the end of this journey, you will understand how these mysterious powerhouses have shaped the entire universe we see today. How does a black hole's feeding frenzy trigger the birth of new stars? And what are the colossal winds that can strip a galaxy of its very building blocks? What does the silent giant at the heart of our own Milky Way reveal about the violent history of all galaxies? Think of a galaxy not as a simple, tranquil island of stars, but as a vast cosmic city, perpetually under construction and demolition. At the very heart of this city lies a unique and powerful mayor, a supermassive black hole. When this mayor is actively receiving tribute in the form of gas and dust, the entire city transforms into what astronomers call an active galactic environment. The central black hole, now an active galactic nucleus, becomes a brilliant beacon of energy, so powerful it can outshine every single star in the galaxy combined. This is not a gentle light. It is the roaring output of a cosmic engine, a testament to the incredible forces at play as matter spirals into oblivion. This intense activity sends shockwaves through the entire galactic ecosystem, heating the vast clouds of gas between the stars and dictating the pace at which new stellar neighborhoods can form. Understanding this dynamic definition is our first step. It shifts our perspective from seeing galaxies as frozen snapshots to recognizing them as living, breathing entities, whose long-term fate is written by the engine at their core. This central engine is an object of almost unimaginable density, a gravitational anchor so powerful it warps the very fabric of space and time around it. We are speaking of a supermassive black hole, a cosmic titan with a mass ranging from millions to billions of times that of our own sun. It does not simply sit passively at the center, it actively governs the galactic domain. The true power of this monster is unleashed when vast rivers of gas and dust are pulled by its immense gravity, spiraling inward at nearly the speed of light. This infalling matter does not fall straight in. Instead, it piles up into a flattened, superheated whirlpool known as an accretion disk. Friction within this disk heats the material to temperatures so extreme that it does not just glow. It screams, emitting a ferocious blast of radiation across the entire electromagnetic spectrum, from radio waves to visible light to powerful X-rays. This is the brilliant beacon we observe, the signature of an active galactic nucleus. Yet this engine does not run smoothly. Its power output is wildly variable, flickering and flaring as it consumes matter in fits and starts. These fluctuations are not just minor details. They are the heartbeat of the active galaxy, directly influencing the long-term evolution of everything around it. The energy pouring from this central engine is so immense that it can push and heat gas across tens of thousands of light years, effectively setting the thermostat for star formation in the entire galaxy. The behavior of this single, invisible point dictates the ultimate fate of hundreds of billions of stars, a profound connection between the very small and the impossibly large. This relationship manifests in several distinct ways, revealing the different forms this cosmic activity can take. The brilliance of an active galactic nucleus is not a single, uniform beacon. Instead, astronomers have discovered a whole cosmic zoo of these objects, each with its own startling personality. We classify them based on the unique light signatures they emit, creating categories like Seyfert galaxies, quasars, and blazars. A Seyfert galaxy might look like a normal, tranquil spiral, but its heart betrays a different nature, shining with a star-like core so bright it can drown out the light of its billions of stars. Its spectrum reveals the frantic, superheated gas swirling in that central whirlpool. Then there are quasars, the true titans of this zoo. These are the most persistently luminous objects in the entire cosmos, so brilliant they can be seen from over 10 billion light-years away. A single quasar can outshine 1,000 galaxies, its light a fossilized message from when the universe was young and chaotic. But perhaps the most dramatic members of the family are blazars. These objects appear to flash and flare with unpredictable violence, their brightness changing drastically over days or even hours. This wild behavior occurs because a blazar has its most powerful feature, a pair of matter jets traveling at nearly light speed, aimed almost directly at our telescopes. We are staring straight down the barrel of a cosmic cannon. This incredible diversity is not merely for our cataloging convenience. It represents a profound truth about perspective and power. The different types we see are often the same fundamental engine, just viewed from different angles and at different stages of its life. A quasar might be a young, gluttonous black hole seen from the side, while a blazar is an older, more focused version seen head-on. By studying this entire menagerie, we can piece together the complete life story of these cosmic engines, from their violent youth to their more subdued maturity. This classification forces us to confront the immense, almost incomprehensible timescales over which these transformations unfold, a journey that spans billions of years. The brilliant flare of a blazar and the steady glow of a quasar are not fleeting fireworks. They are the slow, deep breaths of a cosmic giant. To truly understand the transformation of a galaxy, we must abandon our human sense of time and learn to read a cosmic clock. These clocks are not built from gears and springs, but from the ancient light of quasars observed at immense distances. When we peer at a quas, our 10 billion light-years away, we are not just seeing a distant object. We are receiving a message from the universe's youth, a fossilized snapshot of how things were 10 billion years ago. By comparing this ancient galaxy to one closer to us, we are effectively placing two frames from a cosmic movie side by side. We see the galaxy in its violent, energetic youth, and then again in its more settled middle age. Only by assembling countless such frames can we begin to perceive the grand narrative of galactic life and death, a story written over billions of years. This long-term view is the only way to separate a momentary tantrum from a genuine, lasting change in a galaxy's character. It reveals a slow, relentless dance where the central black hole and its host galaxy are partners, locked in a gravitational embrace that dictates their mutual evolution. One of the most dramatic moves in this dance is a process known as galactic feedback, where the galaxy's central engine directly shapes its own future. This galactic dance between creation and destruction is governed by a single, powerful rule. The supermassive black hole at the center actively regulates the birth of new stars. Think of the vast clouds of cold gas scattered throughout a galaxy as its nursery, the raw material from which new suns are born. The incredible energy pouring from the active nucleus acts like a cosmic thermostat for these nurseries. It heats this cold gas to such extreme temperatures that the clouds cannot collapse under their own gravity, the essential first step in forming a star. In the most energetic cases, this process does more than just heat the gas. It violently pushes it away, blowing it clear out of the galaxy entirely. This is the cosmic process astronomers call quenching. It is the slow transformation of a vibrant blue spiral galaxy, rich with young stars and stellar nurseries, into a quiet red elliptical galaxy, where star formation has effectively ceased. The galaxy is still filled with ancient stars, but it has entered a long, quiet retirement. Its days of vigorous creation are over. Yet, the story is not so simple. This cosmic engine has a dual nature. While its broad winds can sterilize a galaxy over billions of years, the shockwaves from its more localized outbursts can have the opposite effect. These powerful pressures can slam into nearby gas clouds, compressing them so forcefully that they suddenly collapse, igniting a brilliant, short-lived burst of new star formation. So the very same force that can end star birth on a galactic scale can also trigger it in specific, localized fireworks displays. This complex push and pull relationship is what makes active galactic nuclei such a fascinating and critical factor in the life cycle of galaxies. Their influence is not merely destructive. It is a sophisticated form of cosmic regulation. And this regulation is most dramatically delivered through colossal, high-speed winds that flow from the galaxy's very heart. These galactic winds are not gentle breezes, but titanic hurricanes of raw force. Driven by the immense pressure of radiation from the active nucleus, or by the focused power of its relativistic jets, these outflows can hurl matter across space at thousands of kilometers every single second. This is not a slow leak. It is a violent expulsion, a storm that can rage for millions of years. The composition of this wind is what makes it so transformative. It is not just simple hydrogen. It is a rich mixture of gas, dust, and crucially, heavy elements forged in the hearts of stars and stellar explosions. These are the very building blocks for future planets and life itself. When the wind blows, it does not simply move this material around within the galaxy. It can eject it completely, hurling these precious resources out into the vast, empty space between galaxies. This process permanently changes the galaxy's chemical makeup, effectively robbing it of the fuel it needs to build new generations of stars and solar systems. We have seen the evidence with our own eyes, thanks to observatories like the Hubble Space Telescope and the Chandra X-ray Observatory. Hubble has captured stunning images of galaxies where vast bubbles and filaments of glowing gas are being pushed outward, clear signatures of these immense winds. Meanwhile, Chandra's X-ray vision reveals the superheated fronts of these outflows, gas that has been heated to millions of degrees by the shock of the eruption. The sheer scale is almost beyond comprehension. These outflows can extend for tens of thousands of light years, far beyond the visible borders of the galaxy itself. This demonstrates a profound truth. The active nucleus does not just influence its host. It projects its power into the surrounding cosmic environment, seeding intergalactic space with the elemental ingredients for what might come next. Over cosmic time, this relentless stripping of raw material can leave a galaxy anemic and starved, unable to form new stars and destined for a quiet, red retirement. The wind does not just take away a galaxy's future. It can also reshape its very body, sculpting its form in ways we are only beginning to understand. The very structure of a galaxy can be reshaped by the fury at its core. Beyond the winds that strip away its future building blocks, the energetic feedback from an active nucleus performs a more profound act of cosmic sculpture. It can fundamentally alter a galaxy's physical shape, its morphology, transforming it from one type of celestial object into another entirely. Imagine a beautiful, ordered spiral galaxy, its stars tracing graceful, winding arms as they orbit a bright center. This delicate disk structure is a testament to a quiet, settled history. But when the central engine awakens, it injects a tremendous amount of energy into this orderly system. This energy does not just heat the gas, it violently stirs up the motions of the stars themselves. The serene, circular orbits within the disk are disrupted, becoming more random and chaotic. Over billions of years, this relentless churning can completely erase the distinctive spiral arms, leaving behind a much more rounded and featureless form, an elliptical galaxy. This transformation is one of the most dramatic long-term changes we can observe in the universe. It is the difference between a spinning, starry pinwheel and a glowing, amorphous cloud of ancient suns. The final shape of a galaxy is therefore a fossil record, a permanent imprint of its violent AGN history. Powerful computer simulations allow us to watch this slow-motion drama unfold. They show how immense outbursts from the central black hole can puff up the galaxy's central bulge of stars, while simultaneously disrupting and destroying the delicate disk structure around it. This is not a quick process, but a gradual, relentless evolution that plays out across cosmic timescales. The galaxy's very architecture is rewritten by the engine in its heart. This structural transformation is deeply connected to another fundamental change, the chemical evolution we see imprinted in the stars themselves. These cosmic forges do more than just sculpt galaxies, they fundamentally change their chemical makeup. Deep within stars and in the violent maelstrom around a black hole, nuclear reactions act as the universe's ultimate alchemists. They fuse simple hydrogen and helium into heavier, more complex atoms, like oxygen, carbon, and iron. These are the very elements that form rocky planets, and are the essential ingredients for life as we know it. But creating them is only half the story, they must be delivered. This is where the immense power of the active nucleus becomes a crucial distribution network. Those titanic, AGN-driven winds we discussed do not just carry away raw hydrogen, they are loaded with these newly forged heavy elements, spreading them like cosmic fertilizer throughout the galaxy and far out into intergalactic space. Astronomers call this process chemical enrichment, and it is a slow, relentless recycling program that operates over billions of years. With each stellar generation and each outburst from the black hole, a galaxy's overall metallicity, its abundance of these heavy elements, gradually increases. This enrichment is a key piece of the puzzle in understanding galactic ecosystems. The very chemistry that makes our own world possible, the iron in our blood and the calcium in our bones, was likely scattered across the cosmos by such violent events in the distant past. This reveals a profound truth. The relationship between the black hole and its host is not a one-way street of command and control, but a deeply interconnected feedback loop. This intricate dance is so fundamental that it has left a remarkable signature, a cosmic clue etched into the fabric of the universe itself. This deep connection between a galaxy and its central black hole is written into the very numbers. Astronomers call it the M-sigma relation, a name that hides a profound cosmic secret. It reveals a remarkably tight correlation, a direct link, between the mass of the supermassive black hole at a galaxy's core and the mass of the vast swarm of stars surrounding it, the central bulge. This is not a loose suggestion. It is a precise mathematical relationship that appears across the cosmos. A larger central bulge of stars always seems to host a proportionally larger supermassive black hole. This correlation is far too strong to be a simple coincidence. It points to something far more significant, a shared life story. The black hole and its host galaxy did not grow independently, they grew up together, their fates intertwined across billions of years. This is the ultimate evidence of symbiosis on a galactic scale. But how could such a relationship form, with a single, invisible point of immense gravity dictating the growth of an entire galaxy of stars? The answer lies in the very feedback mechanisms we have been exploring. The active galactic nucleus acts as a cosmic regulator. When the galaxy feeds it too much material, sparking a period of intense activity, the resulting outbursts and winds heat and expel the surrounding gas. This action simultaneously starves the black hole of further fuel, calming its fury, and also halts the formation of new stars in the central region, effectively limiting the growth of the bulge itself. It is a self-correcting system, a feedback loop of breathtaking scale. The galaxy provides the food, and the black hole, in its violent consumption, sets the rules for the entire household. This long-term dance ensures that neither partner grows too large too quickly. Their evolution is a coordinated performance, not a solo act. Understanding this symbiosis is the key to unlocking the life cycle of every galaxy we see. Yet, this grand theory, this elegant model of cosmic regulation, raises a very practical question. How can we possibly witness these slow, deliberate changes, these transformations that take longer than our entire civilization has existed? We cannot watch a single galaxy for billions of years. Our challenge is to understand a story that unfolds over eons using only a fleeting moment of observation. The solution lies not in a single telescope, but in a symphony of them, each listening to a different part of the cosmic choir. This is the power of multi-wavelength astronomy, our only window into the long-term dynamics of these active environments. Think of a galaxy not as a single image, but as a complex machine with many moving parts, each part glowing with a different kind of light. To understand the whole machine, you need to see all its components at once. An X-ray telescope, like the Chandra Observatory, peers directly into the furnace. It sees the superheated gas, millions of degrees hot, screaming from the accretion disk and the violent fronts of galactic winds. This is the signature of the most energetic processes at work. But what about the cold, dark dust that hides newborn stars? That is the domain of infrared observatories like Spitzer. Their vision cuts through the cosmic smog, revealing the hidden stellar nurseries that optical light cannot touch. Meanwhile, radio telescopes trace the ghostly pathways of relativistic jets, streams of particles flung across space at nearly the speed of light. And our trusted optical telescopes like Hubble analyze the starlight itself, measuring the motions of stars and gas to weigh the central black hole and map the galaxy's structure. Each wavelength tells a different part of the truth. Alone, they are fragments of a puzzle, but when combined, they create a complete, multi-dimensional portrait of a galaxy's current state. By reading this portrait, by understanding the balance between the furious X-ray heart and the quiet infrared nurseries, we can infer its violent past and predict its quiet future. This multifaceted approach allows us to assemble a cosmic family album, placing young, active galaxies beside old, quiet ones to reconstruct a single, transformative life story. To see how these pieces fit together in reality, let us examine a specific galactic drama unfolding relatively close to home. A mere 47 million light-years away, a cosmic drama is unfolding in the spiral galaxy Messier 77. This is not a tranquil island of stars, but a bustling laboratory where the forces of creation and destruction wage a visible war. At its heart, a brilliant Seyfert nucleus shines, powered by a supermassive black hole feasting on surrounding matter. This central engine is the conductor of the entire symphony, and its influence is written across the galaxy's face in light. The most striking feature is a dazzling ring of newborn stars, a stellar nursery encircling the galactic center. This ring did not form by chance. Astronomers see it as the direct result of shockwaves emanating from the active nucleus. As the AGN unleashes its power, it slams into vast reservoirs of cold gas, compressing them with immense force. This violent pressure triggers a sudden, brilliant wave of star formation, a firestorm of creation ignited by the galaxy's most destructive force. It is a breathtaking paradox, where the same engine that can sterilize a galaxy also sparks new life within it. Yet, look closer at the data, and another, more ominous signature emerges. Spectroscopic observations reveal powerful outflows, torrents of gas being driven away from the nucleus at incredible speeds. These are the very winds we have discussed, the same forces that can strip a galaxy of its future building blocks. In Messier 77, we are witnessing both sides of the feedback loop in a single snapshot moment. The AGN is simultaneously triggering a burst of star formation in a specific ring, while also launching the winds that may, over millions of years, blow away the remaining gas and quench star formation across the entire galaxy. This is the complex, competing reality of galactic evolution. It is not a simple, linear story, but a chaotic and often violent balancing act. The transformation of a galaxy is a battle between opposing forces, and in Messier 77, we have a front-row seat to the conflict. But the most dramatic expression of a black hole's power is not a wind, it is a spear. In certain active galaxies, the central engine does not just radiate energy in all directions. It focuses its fury into two narrow, unimaginably powerful beams, known as relativistic jets. These are not mere streams of light. They are cannons firing a superheated soup of atomic particles and magnetic fields, accelerating them to velocities so close to the speed of light that the laws of physics themselves begin to warp. These jets punch straight through the body of their host galaxy, often extending for hundreds of thousands of light-years into the emptiness beyond. They become intergalactic structures, visible only to radio telescopes as colossal, glowing lobes of energy. Where the tip of this cosmic spear rams into the thin gas that floats between galaxies, it creates a visible shockwave, a wall of energy that heats the surrounding material to millions of degrees. This single action has a profound long-term consequence. By superheating this intergalactic gas, the jet prevents it from ever cooling down, from ever condensing and falling back into the galaxy to fuel new generations of stars. It is a permanent change to the galaxy's environment, sealing its fate from the outside in. Over millions of years, these jets act like cosmic plows, carving out vast, empty cavities in the hot gas that surrounds entire clusters of galaxies. In the most massive clusters we have observed, these jets are the primary source of heat, balancing the natural cooling of the gas and dictating the very thermodynamic state of the entire cluster. They are a testament to the raw, focused power that can be concentrated into a single point. A power capable of regulating not just one galaxy, but a family of thousands. This immense, long-lived activity forces a fundamental question. If this is the engine that drives cosmic evolution, what is its final destination? What is the ultimate fate of such a titanic force? This brilliant phase of activity, this cosmic renaissance, cannot burn forever. The furious ignition of an active galactic nucleus marks just one chapter in a vast, billion-year-long life story. It all begins with a feast, a cosmic banquet for the central black hole. A massive inflow of cold, dense gas is delivered straight to the galaxy's core. One of the most common triggers for this delivery is a galactic collision, a slow-motion merger where two entire star systems gravitationally intertwine. During this immense celestial dance, vast reservoirs of gas are shaken loose from their orderly orbits and sent spiraling inward, directly onto the waiting supermassive black hole. This sudden, abundant fuel supply ignites the engine, switching the nucleus from a quiet slumber to a brilliant, active state. For a time, the galaxy is remade. The AGN blazes with the power of 1 trillion stars, its winds and radiation reshaping everything around it. This period of intense activity is not brief by our standards. It can dominate the galaxy for tens or even hundreds of millions of years. But like any fire, it cannot rage indefinitely. The very feedback processes it unleashes begin to starve it. The powerful winds driven by the AGN's radiation blow away the remaining gas clouds, clearing out the very fuel that sustains it. The black hole, having gorged itself, effectively shuts off its own food supply. With the fuel depleted or expelled, the furious accretion slows to a trickle. The brilliant accretion disk fades, the relativistic jets power down, and the roaring beacon of the active nucleus falls silent. It enters a dormant state, becoming a quiet supermassive black hole like the one at the heart of our own Milky Way. Yet the galaxy it leaves behind is permanently altered. Its structure may have been reshaped from a spiral to an ellipse. Its star-forming gas may be largely depleted, and its chemical makeup forever enriched. This cycle, from a quiet slumber to a violent awakening and back to a final, feedback-induced dormancy, is the fundamental heartbeat of galactic evolution. It explains why we see such a diversity of galaxies in the sky today, some vibrant and blue with young stars, others red and quiet in their retirement. Each is a snapshot from a different point in this grand, transformative cycle, a single frame in the epic movie of cosmic life. Galactic mergers are the ultimate cosmic spark, igniting the brilliant fire of an active nucleus. When two galaxies drift into a gravitational embrace, their slow-motion collision is far more than a simple rearrangement of stars. It is a fundamental disruption of an entire celestial ecosystem. The graceful spiral arms are torn and stretched into long, streaming tails of stars, while vast clouds of gas, once the calm nurseries for new suns, are violently shaken. This chaos is the key. The random motions of individual stars are redirected into a coordinated inward flow, as if a cosmic river has been unleashed. This river of gas, containing the mass of millions of suns, is funneled with relentless precision directly toward the waiting supermassive black holes at the galaxy's cores. The sudden, overwhelming influx of fuel is like throwing gasoline on a smoldering ember. The black hole's accretion disk erupts into a blazing beacon, transforming the galactic center into a brilliant quasar. This is the trigger for the entire transformative cycle. The merger does not just provide the fuel, it also primes the galaxy for the feedback to come. The collision softens up the entire structure, making its gas clouds more vulnerable to being heated and expelled by the resulting AGN's powerful winds. Advanced computer models allow us to witness this entire process unfold in a sped-up cosmic simulation. We can watch as two distinct spiral galaxies approach, their gravity weaving intricate bridges of gas and light. The simulation shows the moment the gas begins its fatal plunge toward the center, and we see the brilliant flare of the newborn quasar ignite, its radiation beginning to push back against the very chaos that created it. This virtual laboratory demonstrates how the violent history of galaxy collisions is permanently recorded in two ways: in the present-day shape of the merged galaxy, and in the past activity level of its now dormant black hole. But this immense influx of gas presents a cosmic question. What happens to all the material that avoids the final plunge into the black hole's grasp? Not all the gas funneled toward the galactic center ends its journey in the black hole's grasp. A vast amount of this material avoids the final plunge, instead piling up in a dense, donut-shaped structure that encircles the central engine. Astronomers call this the circumnuclear torus, a colossal ring of gas and dust that acts as both a shield and a reservoir. This torus is so thick and opaque that it can completely hide the brilliant accretion disk from our view, leading us to classify some active galaxies as hidden or obscured. Whether we see the AGN's full fury or just a glimpse of its reflected glow depends entirely on our viewing angle relative to this cosmic barrier. But this torus is not a permanent fixture. It is a dynamic and evolving structure, caught in the crossfire of the very engine it surrounds. The intense radiation pouring from the AGN exerts an outward pressure, a relentless force that can slowly erode the torus, blowing its material away over millions of years. In other dramatic moments, the powerful outflows from the nucleus can scour it clean, effectively dismantling the black hole's own hiding place. Yet, there is another, more creative fate for this accumulated matter. The same forces that compress gas clouds in the wider galaxy can also trigger collapse within the torus itself. This can ignite a spectacular circumnuclear starburst, a brilliant ring of star formation happening impossibly close to the galactic core. Here, the black hole's influence becomes a paradox, its destructive power inadvertently forging new suns in a final, concentrated burst of creation. The ultimate dissipation of this torus is a critical turning point in the life of an active galaxy. Once this vast reservoir of gas is depleted or dispersed, the central engine begins to starve, its brilliant activity fading into a more stable and quiet state. This slow transformation of the circumnuclear environment directly dictates the kind of feedback the AGN can exert. A galaxy with a dense, intact torus will experience feedback very differently from one where the torus has been blown clear, revealing the naked quasar within. This intricate dance between the black hole and its immediate surroundings proves that the AGN's influence, while born in the heart of the galaxy, does not remain there for long. Its effects ripple outward, shaping the entire galactic ecosystem. The space between galaxies is not truly empty. Within the vast clusters that bind thousands of galaxies together, a thin, superheated gas permeates the darkness. This is the intracluster medium, a ghostly atmosphere of matter so hot it glows only in high-energy X-rays. For decades, astronomers faced a puzzle. This gas should have cooled down over billions of years, condensing and flowing inward to fuel a frenzy of star formation in the cluster's central giant galaxies. Yet this predicted deluge, this so-called cooling flow, was nowhere to be found. The central galaxies remained surprisingly quiet and starved. Something was preventing the gas from cooling. A cosmic thermostat was actively heating the entire cluster. The culprit was the collective fury of active galactic nuclei. The colossal jets launched by these central engines act as intergalactic blowtorches. They punch far beyond their home galaxies, ramming into the intracluster medium and depositing staggering amounts of energy. This injection of heat creates vast, buoyant bubbles that rise through the cluster's atmosphere, stirring the gas and keeping it perpetually hot. This is feedback on the grandest possible scale. The AGN, in its violent outburst, is not just shaping its own galaxy. It is regulating the thermodynamic state of an entire metropolis of galaxies. It prevents the central galaxies from growing too massive, too quickly, by cutting off their external fuel supply. This long-term balancing act is so precise that it maintains the cluster in a stable, steady state for billions of years. To witness this cosmic equilibrium in action, we must look to the most advanced simulations we can create. These virtual laboratories built inside supercomputers are our only window into the billion-year dance of galaxies. Since we cannot watch a single galaxy evolve, we must instead create a digital universe, a vast cosmic simulation governed by the unbreakable laws of physics. Every single particle of virtual gas, every point of starlight, and every ounce of the black hole's immense gravity is mathematically defined and tracked as it moves through cosmic time. The simulation must account for the crushing force of gravity pulling matter together, the complex fluid dynamics of swirling gas clouds, the blistering pressure of radiation, and the explosive feedback from the active nucleus itself. This is not a simple animation, it is a rigorous computational experiment. We can input a young, gas-rich galaxy and then run the simulation forward, testing different theories of how the central engine interacts with its host. What happens if the AGN feedback is weak? The galaxy might form stars in an unchecked frenzy, becoming far too massive, a type of galaxy we rarely observe. What happens if the feedback is too strong? It might blow all the gas away prematurely, leaving a small, stunted galaxy, another outcome that does not match the real cosmos. Only when the simulation includes the precise, self-regulating balance of AGN feedback do we see a galaxy grow and mature in a way that perfectly mirrors the real universe. These models have been pivotal in solving a long-standing mystery, the missing massive spirals. They showed definitively that without the regulatory pressure of an active nucleus to quench star formation, the universe would be filled with enormous, blue, star-forming galaxies that simply do not exist in the numbers we see. The simulation proves that the black hole's fury is the essential brake that prevents galaxies from growing out of control. This virtual evidence allows us to rewind the cosmic clock, to journey back to the primordial universe and witness the very first ignition of these cosmic engines. These brilliant beacons from the cosmic dawn challenge everything we know about growth. The most distant quasars we observe are fossils of light, their images captured when the universe was an infant, less than a billion years old. To see such colossal supermassive black holes already fully formed in this primordial era is like finding a skyscraper in the middle of an ancient, untouched wilderness. It defies expectation. How could gravitational titans weighing billions of times our sun's mass assemble so quickly after the Big Bang? Their very existence tells us that the early universe was a far more violent and efficient nursery for these monsters than anything we see today. These were not the regulated engines of modern galaxies. They were unchecked furnaces, feasting on a dense, rich soup of primordial gas. Their transformative effects, the feedback and the winds, began operating on the very first generations of galaxies, setting the rules for cosmic structure from the very beginning. This was the era of foundational violence, where the first active nuclei carved out the initial hierarchies of the cosmos. Their influence extended far beyond their own galactic borders, performing one of the most important tasks in cosmic history. The intense, hard radiation from these early quasars blasted through the surrounding fog of neutral hydrogen that filled the infant universe. This process, known as reionization, was like turning on a cosmic light in a vast, dark room. The radiation stripped electrons from their atoms, transforming the universe from an opaque, murky sea into the brilliant, transparent expanse we can now observe with our telescopes. These active nuclei were not just shaping galaxies, they were clearing the cosmic stage itself, making the universe observable for all that would follow. By studying these high redshift AGN, We are looking at the architects of transparency, the forces that literally defined how we see the cosmos. This historical context is not just about the past, it is the key to understanding the present. The quiet galaxy next door, with its dormant black hole, is a direct descendant of that foundational chaos. Its current state, a direct result of the violent processes ignited over 13 billion years ago. Our own cosmic neighborhood tells the final chapter of this story. The Sloan Digital Sky Survey has meticulously mapped the local universe, creating a detailed census of galactic hearts. What it reveals is a population of quiet giants. The brilliant quasars and flaring blazars of the ancient cosmos are largely absent here, replaced by a menagerie of low-luminosity active nuclei and dormant supermassive black holes. This is not a gallery of freaks, but a retirement community for cosmic engines. The census data confirms a profound truth. Nearly every massive galaxy we see around us, including our own Milky Way, shows signs of a violent AGN phase in its deep past. This activity is not a rare celestial disaster. It is a universal rite of passage for galaxies. The properties of these local AGN are like the final pages of a biography. Their low accretion rates tell us the great feasts are over. The types of galaxies they inhabit, now often quiet ellipticals or gas-poor spirals, reveal the lasting structural impact of their past outbursts. And subtle signatures, like faint X-ray bubbles or slight disturbances in stellar motions, are the ghostly echoes of the powerful feedback that once shaped them. This present-day snapshot is the direct result of all the transformations we have discussed. The quenching, the sculpting, the chemical enrichment, all frozen in time. We are living in the cosmic aftermath. So what comes next for these slumbering titans? The cycle may not be over. A future galactic merger, or a slow, steady trickle of gas, could reawaken the engine, starting the entire magnificent, destructive, and creative process anew. The brilliant age of quasars is already behind us. We are living in a cosmic epilogue, watching the final embers of a fire that blazed across the early universe. As the cosmos continues its relentless expansion, galaxies are being pulled ever further apart. This grand distancing has a profound consequence: it starves the engines. The rivers of cold, dense gas that once flowed freely into galactic centers are drying up. Major galactic collisions, the spectacular events that trigger the most violent AGN outbursts, are becoming rare cosmic performances. The fuel for the fire is simply running out. The future of our universe is one of increasing quiet. It will be dominated by the dormant supermassive black holes we see around us today, slumbering giants in aging stellar cities. The frenetic transformations we have explored, the furious feedback and the brilliant starbursts, are the closing scenes of a cosmic drama that reached its climax billions of years ago. What remains is the legacy, a population of red and dead galaxies. These are the elliptical and spheroidal galaxies where star formation has been permanently quenched. Their vibrant blue light faded to a dull, cool crimson. They will continue to orbit in the deepening cosmic night, their stars slowly burning through their final reserves of fuel, destined to fade over trillions of years. This is the ultimate long-term transformation, the final state toward which all the violent activity has been steering the cosmos. Yet our quest to understand this grand narrative is far from over. A new generation of observatories is poised to peer deeper into this story. The James Webb Space Telescope, with its infrared eyes, is looking back to the very first ignitions of supermassive black holes, seeking to understand how they grew so fast. The upcoming Nancy Grace Roman Space Telescope will conduct vast surveys, mapping the large-scale structure of the universe to see how AGN feedback has sculpted the cosmic web itself. And here on Earth, immense facilities like the extremely large telescope will directly image the environments around nearby supermassive black holes, watching their subtle flickers to understand the final whispers of accretion. These tools are not just about looking back, they are about reading our own cosmic destiny. By deciphering the life cycle of active galaxies, we are learning the ultimate fate of all galactic structures, including the quiet spiral we call home. The James Webb Space Telescope is not just an instrument, it is a time machine. Its infrared gaze cuts through the cosmic dust that has long obscured our view of the universe's first chapters, revealing the nurseries where the earliest supermassive black holes were born. We are witnessing, for the first time, the ignition of those primordial engines, seeing how they lit up amidst the thick clouds of gas in infant galaxies. This clarity is transforming our understanding of their growth, showing us the specific conditions that allowed these titans to form so astonishingly fast. But Webb is only the beginning of this new observational era. On the horizon are even more specialized tools designed to dissect the intricate dance of galactic feedback. A proposed observatory called Lynx would have vision sharp enough to map the superheated gas in AGN winds with exquisite detail, tracking how this material moves and interacts with its surroundings. Meanwhile, the Square Kilometre Array, a colossal network of radio antennas, will trace the faint magnetic fields that channel and focus the relativistic jets, understanding the invisible forces that guide these cosmic spheres. Together, this next generation of telescopes will work in concert, observing the same galaxies across different wavelengths simultaneously. This multi-messenger approach is like having a complete diagnostic suite for a galactic engine, allowing us to see the fuel, the exhaust, the heat, and the magnetic fields all at once. With this unprecedented precision, we can finally test our grand theories of long-term transformation. We will watch feedback in action, measuring whether the models of quenching and enrichment hold true across cosmic time. This rigorous testing will either confirm our understanding of galactic life cycles, or, more excitingly, it will reveal entirely new and unexpected phenomena that challenge our fundamental assumptions. The hunt is already on for the most extreme outliers, black holes that defy our current classifications or exhibit feedback of a magnitude we have never seen. These strange objects are the key to unlocking deeper truths, the exceptions that force us to rewrite the rules. Our maps of the cosmic landscape are about to be redrawn with finer ink, revealing details we could only guess at before. Even our best models of galactic evolution are sometimes broken by the cosmos itself. Across the universe, astronomers have found bizarre objects that defy our established rules, galaxies that behave in ways our current theories cannot fully explain. Consider the case of a galaxy with all the hallmarks of intense AGN activity, brilliant radiation and powerful winds. Yet when we look for the central supermassive black hole, the gravitational anchor is mysteriously absent or impossibly small. How can an engine roar without a visible furnace? One compelling possibility is the existence of intermediate mass black holes, celestial objects that bridge the gap between stellar remnants and the supermassive titans. These missing link black holes could be powerful enough to drive activity, yet remain hidden from our current detection methods. Then there are systems where the feedback is simply too strong. The galactic winds are far more energetic, and the relativistic jets far more powerful than the mass of the central black hole should allow. It is like a small campfire generating the heat of a volcanic eruption. This forces us to reconsider the fundamental physics of the accretion process itself. Perhaps there are more efficient ways for matter to transfer its energy, or maybe magnetic fields, twisted and amplified to unimaginable intensities, are acting as cosmic slingshots, launching material with far greater force than we thought possible. These outliers are not mere curiosities. They are the signposts pointing toward a deeper truth. Every time our elegant framework is challenged by a strange new discovery, it pushes us to refine our understanding of the cosmic rules. The pursuit of these anomalies is not a side project in astronomy. It is the very engine of scientific revolution. It compels us to ask the next, most profound questions about the universe we inhabit. The very physics that governs the space around a black hole remains one of our greatest challenges. We can model the vast, galaxy-spanning winds, but connecting them directly to the chaotic maelstrom of the accretion disk is like predicting a hurricane's path by studying the first swirl of water down a drain. The churning plasma in that disk, twisted by magnetic fields of almost mythical strength, must somehow launch and sustain these colossal outflows. How does energy transfer from that tiny, violent region to reshape an entire galaxy? We simply do not yet have the complete picture. These magnetic fields are likely the hidden architects of the entire system, acting as cosmic conduits that channel the black hole's power. They might be the reason some engines fire focused jets, while others release their energy in a more spherical blast. Unraveling their precise role requires more than just better telescopes. It demands a fundamental leap in our theoretical understanding of plasma physics under conditions we cannot hope to recreate on Earth. This pursuit pushes at the very boundaries of known science. The dynamism of this field means that every answer uncovers two new questions, a testament to the profound complexity of the cosmos. And the implications of this quest are not confined to distant quasars. The silent giant at the heart of our own Milky Way, Sagittarius, a star, is a case study in this very mystery. Its current quiet state, punctuated by faint, unexplained flares, is a direct result of the same ignition and shutdown processes we are trying to understand in faraway galaxies. By solving the puzzle of these cosmic engines, we are ultimately writing the history of our own galactic home, learning how it came to be the quiet spiral we inhabit today. Our own galactic home holds a silent secret. At the heart of the Milky Way lies Sagittarius, a star, a supermassive black hole currently in a state of deep slumber. Its present quiet is deceptive, a calm that belies a more vigorous past. The evidence for this ancient activity is written across the sky in high-energy light. Soaring above and below the galactic plane are the Fermi bubbles, two colossal structures of gamma-ray emission that stretch for 25,000 light-years each. These are not static features. They are the ghostly remnants of a powerful outburst, the cosmic echo of a time, millions of years ago, when our own central engine roared to life. The precise trigger for that eruption remains a topic of intense study. It might have been a sudden influx of gas from a disrupted star cluster, or perhaps a smaller galaxy was drawn into our own, its material funneled toward the center. Whatever the cause, the result was a dramatic, if temporary, transformation of our galactic core. This direct connection changes our perspective entirely. The long-term transformations we observe in distant, brilliant quasars are not just abstract events happening to others. They are part of our own inheritance. The Milky Way is not a timeless, unchanging island. It is a dynamic entity with a biography, a story that includes chapters of violent activity that helped shape the very galaxy we call home. The Fermi bubbles are a permanent part of that legacy, a reminder that our quiet neighborhood was once sculpted by the same forces we see shaping the cosmos today. This understanding brings our exploration to a profound and humbling conclusion. The silent giant at our galaxy's center is not an exception to the rule, but a living testament to it. Our journey through these cosmic engines reveals a universe not of static islands, but of dynamic, living systems. At the heart of this grand narrative is a powerful symbiosis, a deeply interconnected dance where the supermassive black hole and its galaxy grow and evolve together across billions of years. These active nuclei are not mere anomalies. They are fundamental architects, shaping galactic destiny through a series of profound and lasting transformations. They regulate the very birth of stars, turning vibrant spirals into quiet, red ellipticals. They drive colossal winds that strip galaxies of their future building blocks, while simultaneously seeding intergalactic space with the heavy elements essential for planets and life. They even reshape a galaxy's physical form, sculpting its structure from the inside out. Every process we have explored, from the brilliant ignition of a quasar to the final whisper of a dormant giant, has played a role in crafting the diverse cosmic population we survey today. The great astronomer Carl Sagan once reflected that the cosmos is within us, that we are made of star stuff. We now understand that this very star stuff, the iron in our blood and the calcium in our bones, was likely scattered across the universe by the immense power of these active galactic engines. Their long-term transformations have not only built the galaxies, they have forged the essential ingredients for us to exist. As you reflect on this journey, we would love to hear which transformation captured your imagination the most. Was it the galactic winds that can sterilize an entire galaxy, or the paradoxical trigger of new star birth? Share your thoughts in the comments below. If these deep dives into the mysteries of our universe fascinate you, be sure to subscribe for our next exploration.